small workshop we organized with Martin, just taking advantage of the various visits that we have with me, Johannes, Francisco, Johannes and Francisco Rojas. So we decided just to organize something. And the workshop is about perturbative and imperturbative methods. Yeah, this is a very broad range of topics, so we expect the talk to be as pedagogical as possible, and we are so just to communicate your ideas to people.
There is not many discussions, so please feel free to ask during the talks, after the talks.
So
be very relaxed.
We chose this format that what I hear today is here in Samba, tomorrow. We have two talks in the morning. Well, the afternoon, today in the afternoon is a poster session. Posters. Thank you, the speakers, and Martin is going to share
the first talk by Daniel Florian. That's about precision.
Okay, thanks a lot, and welcome also to the university. This is not looking well, I think. Let me see. We are missing. Okay, I wanted to put all the, institutions related. I forgot La Plata, but I thought that the most relevant one was Munich, and then here you have the official. It's true, no? There are 6 official beers in Munich that are accepted by the government, and they are all very good. So my talk will be. I'm not going to talk about my work. Actually, I will try to do a summary of what is the situation in precision in perturbative QCD for the audience, which I think might be more useful than talking about what I did recently. So let me start by saying that when you look at the data from the LHC, everything looks standard model-like. I always liked this chapter from a string theory book that had only one page about the direct experimental evidence for string theory. Well, you could do the same for the failure of the standard model, which is actually not completely true because we are hiding a number of things, right? I mean, I don't know if she minus 2 for the muon there is something or not. That is not completely clear, but we know that neutrino has masses that is missing dark matter that we don't know which is the origin. So the standard model is not complete. But in any sense, when you look at the LHC data, what you find is something like this. We find that if you measure cross-sections over more than 12 orders of magnitude of different processes and compare to the theoretical calculations, the agreement is impressive. So the standard model does predict what you see in the experiment very well. Also, if you look at even more precise extractions that corresponds to global electroweak fits, you will always find that, well, there are a couple of observables with 2 sigma pool from one side to the other, but everything seems to be in perfect agreement. So much that some time ago I thought that we should call the standard model the GOAT, the greatest of all theories. And if you had to compare the success of the standard model to the success of an individual in this planet, I think the only one that would fit would be Messi with all these trophies. And you could say that the Higgs boson, finding of the Higgs boson was like getting the World Cup. I know that it's been a long time since we won the World Cup, but we're still champions, and we should remember our friends from other countries that this is still the situation. So anyway, even though everything looks standard model-like, we know that there is plenty of room for new discoveries, and I think there are 2 main extreme scenarios for new discoveries. One is the one that we will all like, that if we are able to excite some new particle at the LHC, then at some point, and if we can generate enough statistics to see it, we would be looking for something like this, like a resonance in invariant mass or a large PT distribution, in the same way as the Higgs boson was found, and then you can claim that you have found a new state. And for that, you don't really need a very precise theoretical calculation for the background because you know how to do things on both sides of this peak. So this is pretty much independent from the theoretical prejudices, I would say. You need a descriptive theoretical calculation in order to understand more or less the background. But it turns out that this is not the situation right now, and what we have been looking for several years, and probably will be the situation for the next couple of decades, is that we might be looking for new interactions. Oh, that's not. For new interactions, in a sense that we will be looking for a small deviation from the standard model calculations in the data. So suppose that you look at some large PT distribution for some process, and then you're able to compute the cross-section that the theoretical calculation is this green band that includes the central value and the theoretical uncertainty. And then at some point you can collect enough data in order to show that there is a deviation from there, then you would be able to say that you found something there. You don't know exactly what it is, then you will need a effective field theory description, some particular BSM model, but it is clear that for that you need precision, both from the experimental point of view and from the theoretical calculation, because if your calculation has this uncertainty, then you wouldn't be able to say anything about any possible deviation. So I like to say that precision is the name of the game for the next decades, and if I had to bet my salary about what would be the way to find new physics at the LHC, I could bet it completely into this idea of finding new interaction. Of course, it's very easy to bet an Argentinian salary for something that will be checked in 10 years, and who cares, right? I will pay it in pesos. But this is the situation now. And the point is that for precision, you need QCD, because in the LHC, QCD is everywhere. Every time we look at some observable that could be jet production, Higgs, photons, gauge bosons, whatsoever, everything starts with the collision of two protons and then with the partons inside the protons. And let me just remind you that anytime we compute a cross-section at the LHC, a hadronic cross-section, what we have to do is a convolution between the parton distributions, the non-perturbative objects. I will go into slightly more detail in one slide about them, but they basically give the probability of finding a quark or a gluon inside the proton with a certain momentum fraction, times the quantity that we can compute in a perturbative expansion, which is the partonic cross-section. Of course, there are corrections which are related to the energy of the process, but in principle, this is quite accurate, and this is the kind of calculation that has been used to compare to experimental data in the previous plot. So it's clear that you need precision for both, for the perturbative calculation, but also for the non-perturbative parton distributions. And let me just remind you very briefly which is the situation on the parton distributions. The parton distributions are based on the parton model, and especially on what we call factorization, on the idea that when we have a process that involves different scales, one scale is the scale of the process itself. For instance, deep elastic scattering could be the virtuality of the photon, in Reliant, the mass of the W boson, and so whatsoever. And then there is a much smaller scale, which is related to lambda QCD, to the structure of the proton. So the idea of factorization is that you can separate these two effects, that you can put all which is related to the large distances in this parton distribution, the probability of finding a given parton, could be a quark, antiquark, a gluon, with a certain momentum fraction set in the proton, and then is this multiplied by the partonic cross-section, which is computed perturbatively because it involves only small distances, large energies. And in this case, it will be, if we are doing electron-proton into electron, that would be electron-quark, where the quark here carries a momentum fraction set of the initial proton. Now, these parton distributions are quantities that we cannot compute in a perturbative way because of this small scale, but they have a very important advantage, is that in principle they are universal, in the sense that they are dependent only on the structure of the proton and not on the structure of the particular collision we are looking at. And therefore, we can in principle extract them from one observable and then use it to compute another one. And this is how things work. Let me just remind you also that this parton distribution not only depend on the momentum fraction, but also depend on the typical energy scale, which is a kind of resolution of the structure of the proton. We cannot compute the dependence on the momentum fraction, but we can compute the dependence on the scale by the Altarelli-Parisi equations, which are very well known. So how do you do to, just in one slide, to get these parton distributions? Basically, you do the following. You parameterize them by some ansatz, Could be this, could be a neural network, more complicated stuff, but in principle, there are a number of coefficients here, A, alpha, beta, that you don't know. You give them some initial value, you evolve this Parton distribution until you get the typical scale of the process you are interested in using the alternative Paris equations. You compute the chi-square, that is, you compute the observable at that scale, you take the difference with the experimental result, and you compute the chi-square. And then what you do is you repeat several times this procedure by changing these parameters until you find the one that minimizes the chi-square. That's basically the idea. That defines the best set of Parton distributions. And then you can do the same by doing variations of the data in such a way that you can also provide not only the central value for the Parton distribution, but also a typical understanding of the statistical uncertainty from them. Now, there are several groups doing this. Just to give you an idea, if you have never seen them, this is how they look like at the scale of 10 GeV or 10 to the 4 GeV square. But the idea is basically the following. If you look at the valence distributions, the U valence and the D valence, they basically have a peak around 1/3 because they contain the flavor structure of the proton. There are 2 U's and 1 D. There are, if you go to very small momentum fractions, then you find that there are many antiquarks, and what you most found is that the proton is basically full of gluons. Check that this has been divided by 10, so the gluon distribution is 10 times larger than any other distribution when you go to, say, x equal to 10 to the minus 3, which is a typical scale that is being explored, this region, by the LHC. And therefore, every time you have a collision, if your process can be produced by gluons, then will be produced by gluons most of the time, okay? Higgs is one case in which the Higgs boson is 90% of the time produced by gluon fusion because of the large amount of gluons in the proton. So what is the state of the art? There are many groups doing this analysis of Parton distributions already at next to D in order. That means to order alpha S square compared to the leading order here.
As far as I understand from what they are saying, here you are using experimental data to fit.
Exactly.
Is there any method to compute them from first principles without using experimental data?
Well, in principle, it's always promised that lattice should be able to compute it at some point, but in the real life, they haven't been able yet to do calculation that exactly corresponds to the Parton distribution that are being defined here. And also it's very difficult to reach the typical uncertainty, very small uncertainty that they are obtaining already from the fits. So it's not easy to compete with that, but in principle it should be possible to do it. But you have to use a non-perturbative approach. So there are these, those are the main groups that you will find in the literature, particularly those one in red, that are producing fits by different assumptions. So they differ in the way how they fit, how they parameterize the PDF, which coupling constant they use, some constraints from the theoretical point of view, the way they estimate errors, the selection of the data they use. But since these Parton distributions are so relevant, all these people actually met, they meet every 4 or 5 years, and they produce what is called a combination. So they not only fit each of them, the Parton distribution, but they also fit the combination of these Parton distributions, which gives a reasonable idea of the full uncertainty, if you want, on them. And this is one interesting graph. This is, which is the typical uncertainty, the band. You can see here it's 5%, 5% in all of them. So this is the QQ bar luminosity, gluon quark. This one should be. This is QQ bar, and this is gluon. And what you see here is which would be the typical invariant mass of the particle you might be producing at the LHC. And typically, if you're looking for something of the order of TeV, you will see is that the uncertainty coming from the Parton distributions is of the order of 5%, more or less. And this is something which is very difficult to reduce. I mean, because this is mostly depending on statistical uncertainties from the data, but there are still many theoretical uncertainties which are not being accounted by this plot. So things are improving constantly. Every time we get more data from the LHC that can be put into the fit and then produce, in principle, more precise Parton distributions, but the uncertainty is still around there. And this is the typical value of alpha S, what you can see is has an uncertainty below the 1 per mil level, 1%, sorry. Now, which are the news on this market? The news are that mostly that the splitting functions needed to do this evolution of the Barton distributions at next to leading order are basically known to some extent, but with a very good approximation. And now there are people trying to perform fits at NQ below. As you will see, of course, if you want to do a fit at NQ below, then you need to compute all the observables at NQ below, which is not the situation. Right now, there are, I will show you in a moment, that there are only a few calculations that to this order, so people are doing some kind of approximated NQ below just to have an idea of what would be the impact of the next order in the Barton distributions, and they find that in some cases the corrections could be of the order of 5%, so they are of the same order of the typical uncertainty that is being claimed in the Barton distribution. So not easy to get below this 5% level from the non-perturbative part. But of course, more data will be included in the fits in the next decades, and then since there will be better control of theoretical uncertainties, in principle, we might expect a small reduction, but not very large, with respect to this 5% from the non-perturbative part.
There's some logarithmic.
What?
There's some logarithmic terms in that.
Logarithmic in what sense?
Some dependency.
There is a dependence. Yeah, of course, yes. No, the value I put before is the value of alpha S at the mass of the set. So, yeah, no, sure. So in the rest of my talk, I will try to cover, which is probably more interesting for you, which is the perturbative toolkit for precision at colliders. So how do we compute things that, in order to get the precision, which is really needed to compare to the precision of the LHC, which is becoming really accurate, actually. So there are many things that appear here, which I will talk about a few of them, but people are doing QED and electroweak corrections, which start to be relevant. Resummation when there are large logarithmic corrections, Parton shower, automation in order to get these calculations mostly automatic. But of course, everything starts with a fixed order calculation. So we do a calculation as a perturbative expansion in the strong coupling constant alpha S, such that the first order is what we call leading order, next to leading order, next to leading order, and so on. So I will try to give you an idea of which is the situation today and which are the bottlenecks in order to improve this precision. So let me just try to remind you why we need to do that, why we need to go to really high order corrections. One of them is that the corrections are usually large, simply because alpha S is the order of 0.1, and then it also becomes multiplied by some color factor, which is, there is a glue on the color factor if is the number of colors, so it's 3. So alpha S times CA is 0.3, and so it's not a very small quantity in which you can imagine that the conversions of the expansion will be fast, and you will see an example where you really see a very slow conversions. So you really need to go to higher orders just to get a certain level of conversion. Also, because we want to do accurate theoretical predictions, as I told you, it's not just a central value. We need to quantify which is the uncertainty on the calculation. And the usual way to quantify uncertainties is by doing what we call the variation of renormalization and factorization scales. So let me put it in this way. Every time you compute something perturbatively that depends on the coupling constant alpha S depends on the renormalization scale, which is not a physical scale. You will typically choose it like the typical energy of the process or the mass of the object you are producing, but it could be a factor of 2 larger or smaller than that, or 3 or 4 whatsoever. So in some way, by performing variations of the renormalization scale, we have some idea about which is the uncertainty, because if we were able to compute the cross-section to all orders, we know that there wouldn't be any dependence on this scale. So the variation on the scale is somehow a measurement of the size of the terms that we have truncated from the expansion. The first approximation to that. There is also the factorization scale. As I told you, this is the one which is related to the Parton distributions. So the cross-section actually depends on both of them. So we typically change them, and I will try to discuss a bit about that later, whether this is reasonable or not. We take them as a central value, and then you change it by a factor of 2 up and down, and then we produce bands which are related to what we estimate is the uncertainty for the calculation. So for instance, this is a very precise calculation for Drell-Yan. This is the leading order calculation, next to leading order, next to leading. So what you can see is that when you go to higher orders, the dependence on the scales is reduced, which is reasonable because the next orders which you are missing are expected to be small. But also you can see that by performing this variation at leading order, it's not enough to guess what would be the next order, okay? Because there is no overlap between the bands. So sometimes this factor of 2 is not actually not enough. It's only from NLO to NLO that you start to see some kind of conversions. So this is the way we quantify theoretical uncertainty. Another reason to do higher order calculations is that when you go to higher orders, you have more partons in the final state, and then you can reproduce in a better way, which is the experimental condition, in the sense that you're looking for sheds. For instance, a leading order shed is just one parton, and next to leading might have 2, and next to next might have 3 partons, and then you can understand the structure of the shed in a better way. And also there is a possibility of new channels when you go to higher orders. For instance, one very interesting observable is diphoton production, which is the main background for the Higgs boson search. So if you look at the lowest order, the diphoton is being produced by the annihilation of a quark and an antiquark. But if you go to 2 orders higher, then you can find the situation in which gluons can also produce 2 photons. And since gluons are much more copious in the proton than quarks, this order, even though it's alpha s squared suppressed compared to this one, could be numerically very relevant, phenomenologically very relevant. And here is, I think, a very good example of how the precision is being challenged by the experimental data. This is deep elastic scattering, single shed, one shed production and deep elastic scattering. What you see here are the data points from SUS that were obtained in the 90s, okay, so many years ago, 30 years ago. And what you see in different colors are the available calculations. So this is an observable that has been computed to next to leading order. So you have leading order, next to leading, next to next, and Q below. So even look at the red one, which is an estimate of the uncertainty on the I didn't do that. So look at the red one. This is the most precise calculation we have now, and it's possible it will take more than 10 years to get to the next order. But the uncertainty here is extremely much larger than the experimental uncertainty from data obtained in the 90s. Okay, so this is a real challenge in the sense that if we cannot match the experimental precision, then the experimental precision becomes a bit useless because it's completely dominated by the theoretical uncertainty and not by the experimental one. So we are really being challenged by, from the theoretical point of view, by the experiments, in a sense that we really have to improve our results. So it's not just an academic problem that we are interested in going to 3, 4 orders or whatsoever, but it's a phenomenological issue at this point. Now, let me just remind you how you do a calculation. If you want to do a Born cross-section, a leading order, then we know very well how to do it, okay? Just well, scale dependence. In that particular case, I think it's a factorization scale dependence. It's a bit, there is a trick here, of course, that this is in Q below, but that involves parton distributions which are not fit at NQ below. So in principle, there is an uncertainty also from there. Yeah. So there is something missing still. Now, if you want to do a leading order calculation, you know how to do it. You compute the 3-level matrix element for how many partons you need in the final state. You put some measurement function, which is the one that defines observable, how many sheds, which particle, and whatsoever. And then you integrate over the phase space. You can do it with brute force Feynman diagrams, recursive relations. Today, there are fully automated calculations for very large multiplicities. I think up to 20 partons, you can do this calculation in a reasonable way. Of course, it's very simple to integrate. There are no divergences, so it's just a numerical problem if you want to do this integration. But in most cases, the leading order is not enough for precision physics, and actually, the situation is that leading order can be done by ChatGPT more or less right now. I mean, if you, okay, it's a bit tricky, but I asked it, that's something I did 2 years ago, actually. I asked it ChatGPT to write a Fencal code that computes the partonic cross-section for QC into QC scattering. and then to give the result for the cross-section in terms of demand stem variables. The result is wrong, but anyway, I think it is interesting that it can actually produce the code. I mean, and it's not being trained, of course, to do that. So can you imagine that if you train the system just to do Feynman diagrams, then this wouldn't be a problem, actually. But let me see the final result. Oh, it's too slow. It's funny because by the time I was doing the PhD thesis, it was possible to do a PhD thesis computing these kind of things. Of course, you cannot do that anymore because things have become much more complicated. But somehow here is the result, which somebody showed me that it was not completely right. Okay, I asked to assume that the particles are massless. So I think there is some missing term. But anyway, it was funny that it can produce such a thing. Okay. So then the thing is that we have to go to higher orders, and then the question is why going, for instance, to next to in order makes things more complicated. And the main reason, I think, is in principle we could actually blame Feynman. Feynman gave us very interesting tools to do perturbation theory, but there is one issue there, which is related to the fact that the calculation is being done by separating diagrams which contain the same or different number of particles. So if we have to do a calculation, for instance, to do photon quark to quark, at next to the in order, we have to do on one hand the virtual corrections that includes only 3 particles separately, and then we have to do the real correction, which includes 1 extra gluon, and then we have to integrate over this gluon. Of course, we have to integrate over this gluon here also in the virtual part, but these 2 calculations are being done in a separate way, and this is something that people have been trying. I think every 10 or 15 years, somebody tries to modify the way to do this calculation in a way that you don't keep n number of particles, but something like n plus epsilon, for instance. So let's say that if you can manage things, to do things in such a way that if this gluon is very soft or very collinear, then if you can put it here and do this calculation, add these things, both things together, then you would cancel all the divergences that appear in the middle step. But anyway, the usual way we do it is we separate them, we use dimensional regularization, and then we, of course, we deal with the ultraviolet part, which is not a problem in the virtual corrections. We know how to do that. But we know that there are remaining divergences which are related to the soft and collinear configurations, which are, in this case, they give poles of the order of 1 over epsilon squared. It's easy to understand in this case, which is the origin of these poles. If you look at this diagram, when you produce an extra gluon, then there is a denominator here, which is related to this particle, p minus k. So if you consider them massless, this is 2p times k. And then if you write in terms of the energies and angles, you will see that this is something that is going to diverge when you integrate over the momentum of the gluon, anytime the energy of the gluon becomes 0 or this particle becomes collinear to the initial state. Okay, they're in principle one related to the energy of the quark, but the diagram, because of fermion number conservation, will give an extra, at least a square root of energy that will cancel this. But there are 2 configurations, soft and collinear, that give divergences. The same happens here, of course, in the virtual part. And then you compute them separately, we put them together, you add, you show that there is a cancellation of divergences, and then you keep the final part. Of course, you don't want to do that for every observables analytically, because it would be a mess. Every time you change the definition of observable, you would have to do the calculation again. So this is usually done in the semi-numerical way, by using what is typically called the subtraction method. The idea of subtraction method is that if you have the real part, which you know that when you integrate over the phase space will give a divergence, you generate somehow, if you are smart, a subtraction term, which is very simple, but has exactly the same divergences as this quantity. So if you do that, you know that this difference is finite, and then you can compute this in 4 dimensions numerically to evaluate observable. And then, of course, you have to add this one again. If you subtract it here, you add it here, but then you can do this calculation analytically, because it's very general. This has exactly the same properties of the collinears of divergences as the matrix elements, and then you show that there is a cancellation, analytical cancellation, the divergences between these 2 things. You put everything together and you get the evaluation of your result. Now, next to linear calculations were very difficult, actually. Today they seem kind of trivial, but the first next to linear calculation was done by the late 70s, which was the calculation of deep elastic scattering and Rayleigh. It took more than 10 years to do the 2-to-2 process. That means, for instance, PP into 2 sheds. It took more than 10 years to do PP into 3 sheds. So this is typically the time lapse from adding one extra, that means adding one extra particle or one extra loop in case. And it took then more than 10 years to get 2 to 4, and then there was an explosion of calculations. Okay? And today, basically, you can compute almost everything, and next to linear order, almost everything means something which is doesn't have very large multiplicity. If you want to compute 7-shed production, then you will have a numerical issue, but not a technical one, I would say. Or if there are loop-induced processes that start not at a leading order, but at one loop. But in principle, the situation, the idea is that you can do these calculations in an automatic way with zero cost for humans, and this is conceptually solved with many other improvements on that. So just to give you an idea, how easy is to do an extra linear calculation these days? Well, basically, you have to specify the process with an input car, define the input parameters, masses of the particles, energies, and so on, define which are the final cuts, and we have now a number of different codes that can do this calculation for you, not only giving you the central value, but also an understanding of the uncertainties, matching to Parton showers, and so many other things. And they compete on many features. Just to give you an idea, for instance, if you want to do proton-proton into TT bar plus a shed, using MathGraph, which is a code, and this is quite old actually, what you have to do is basically to write this. So you have to define which is, well, you are going to use a standard model. You define which are the particles, which are the sheds. You ask to generate the quantity, get an output, and calculate the cross-section. It takes like 5 minutes to generate the code that will do that. And then you run the code, and in 30 minutes, in 20 cores, which is a simple machine, I would say, you get a very nice distribution for this observable. So it's really a problem that is basically solved. So there is no reason today to do any calculation. Even if you're doing BSM, you need to compute the background. You shouldn't do it at leading order because next to leading is available for almost everything. Okay. Now, then there was, after this automation, there was a revolution at next to leading order, which is becoming now the standard. And here the situation was more or less similar. The first calculation also appears in the 90s. It was Rayleigh, 2-to-1 process, proton-proton into a gauge boson. It took quite more than 10 years until we actually did the first 2-to-2 calculation and next to leading order. The simplest one you can do is 2-photon production. It's 2 particles, but the photons have no color. So in principle, the number of divergences that appear there are less than for the color case. And it took another 10 years to do the 2-to-3, which again is 3-photon production, okay? But you can see that there is a large number of processes that have been computed in the last 2 or 3 decades. And I think it's a rule of thumb is that every time you add an extra particle or an extra loop, more or less 10 years to be able to perform this calculation. And it's something that you can probably imagine about the future in the field also. What is the degree of complexity at next to leading order? Where here the situation is a bit more complicated because there are 3 kind of different processes, if you want, in terms of the number of particles. Suppose that you want to do double gauge production at next to leading order. So you have to do first the 2-loop calculation, okay, which will contain poles, infrared poles up to 1 to epsilon to the 4th. Typically here the bottleneck is the large multiplicities, but there are many available already, of course. Then you have to do 1 loop plus single emission. This is, if you want, the simplest one in a sense that it's a 1-loop calculation. It's a phase integral, phase space integration next to leading order like. So, but the complexity is still the same in the sense that you get a 1 over epsilon square from the loop, and then you will get a 1 over epsilon square extra, multiplying that one by doing the phase space integration. And then there is a double real emission. The double real emission, in principle, is a 3-level calculation. So the matrix element, in principle, is very simple, but it's a hell of infrared singularities because you can get many singularities now that could be double collinear, triple collinear, collinear soft, double soft, etc. So there are many configurations you have to deal with, okay? And also we'll give this 1 over epsilon square poles. I'm going to show only one slide here because you know much more than me about how to compute these things, and I'm sure that Johannes will speak about that. But just to give you a summary of what is available today, the state of the art for two-loop amplitude is, it's amazing what happened in the last couple of decades. Today, what you know is that you can, if you want to compute an amplitude, you know that you can decompose in terms of master integrals times some coefficients. These master integrals are universal. They are the same for every process. The coefficients depend on the process. You can compute by using Feynman diagrams, generalized unitarity, or some fancy things that probably Johannes will, will show us in the afternoon. There are many tools for that, but just to give you an idea, which is available today, which is available are the two-loop amplitudes for 5 massless particles, or even 4 massless and 1 massive. They are all available in the Feno ready form. They are actually being used to do NNLO calculations, and which is new, sum of the amplitudes for the 6 massless. We were discussing with Johannes a few weeks ago in Munich about which is the number, the magic number for that, and I think the magic number was 7, no? That if you add the number of legs plus the number of loops, if you reach 7, that is something that can be done or is already available. If it is 8, which will be this case, 2 loops which is massless, then the situation is a bit more complicated, but... Eh?
7 sounds
It's the magic number, yeah. But it's really amazing that if you look at what was the situation 20 years ago, that was considered to be basically impossible, okay? And today, it's not only possible, you will see things which are even more amazing. So, and there is a lot of improvement in this. Actually, for many years, the bottleneck for the calculations at next to next order was in the virtual amplitude. This is not the case anymore, okay? So the problem is now on the real part, and I will show you in a moment. The problem in the real part is how to handle these singularities. In principle, we know how to do that. We know how to compute the real matrix elements. We know which are all the soft and collinear limits, but the problem is how to handle them, how to generate a subtraction term which has exactly the same singularities as this one, but you can still compute it integrated analytically to cancel the divergences in the virtual part. This is what is the subtraction method. And this is, you can... How do you define S?
What the ambiguity is?
That's, there is a big ambiguity in principle. Since you are adding and subtracting, you can do everything. If, yeah, because you add and subtract the same thing, as long as this quantity in d dimensions, because it has to be done in d dimension, has the same singularities as this one, then you can add a constant term and then nothing will happen, or something which has no divergences. Yeah. Exactly. Exactly. And you can see the ambiguity here. There are many different groups trying to do different subtraction, basically defining different subtraction terms in such a way that they can be integrated. In some cases, you could even try to do this integration numerically, but people still insist on the analytical calculation because of time saving, basically. But there are different approaches, and this integration of subtraction term is quite complicated, okay? There is another method which has been developed over the last year. Because this is a virtual part, so the phase space is different. It has at least one particle less than this one. So what you do actually is you decompose the phase space for the real, because it's the phase space for the real, this is for the virtual. Usually what you try to do is you decompose the phase space factorized in terms of this one times something else. So you integrate this quantity over there, something else, and then you cancel the singularities. Because the other integration is not, in principle, not divergence. There is another way to do that, which is called the phase space slicing, that was used in the 80s. The people abandoned that for next to the order, but it turns out that for some observables can provide very much faster calculations at next to the order. The idea is a bit different. The idea is you know that the real part has some divergent behavior. So let's suppose that we cut the phase space by some parameter. Sometimes we can find one single parameter that can eliminate all the singular configurations, and I put it from 0 from delta. And then I separate the integral from 0 to delta and from delta to 1. And then I can do this calculation numerically. Of course, it will depend on logs of this quantity. If you go to next linear order, it will depend on log of delta to the fourth power. So it's very sensitive to this cut. But the interesting thing is that we know how to obtain this, the rest, from some analytical methods like resummation. So we can write in terms of the resummation that will provide also this log to the fourth power of delta, and then we will have to show, to do a calculation very precise numerically in such a way that this logarithmic dependence is cancelled. So it's like a different regularization, if you want. Okay, instead of regularizing some of the divergences with dimensional regularization, you regularize it with the cutoff. If you are able to manage this cancellation numerically of the cutoff between these two terms, then you can obtain a good result. There has many things against that because of the cancellation, but it turns out that when you are looking for configurations in which there is no color in the final state, or there is only one color particle, then you can do these calculations much faster. In a sense that you will see for the other, you will need a cluster to run the calculation. This one you can run it in the laptop, so it makes a difference in terms of phenomenological analysis. So the summary is that there are several methods which are resulting in many NLO calculations, but my feeling is that more than the refinements that people are doing by defining different subtraction methods, for instance, the most relevant thing will be the efficient implementation, because you will see it could take, some calculations could take 10 to the 6 hour CPU hours, for instance, to get a proper result. Now, there are no automatic NNLO yet, but if you need to do some calculation at NNLO, because you need, for instance, some background, there are codes that already contain a large list of processes that have been computed. Matrix contains many of them, MCFM also. So the simplest processes are already coded there, and you can use to compute your observable. This is one of them, for instance. There are several actually observables. So let me show you one example, 3-shed production at the LHC. So now you proton into 3 sheds. There are 2 calculations available by 2 different groups that they still haven't been able to compare them. Just to give an idea, when this plot was presented by this group, they were using some Parton distributions which were outdated because there was a new set. So somebody asked you why you are using a set of PDFs which was released 3 years ago, because they started to run the code 3 years ago. Okay, so it takes 10 to the 6 CPU hours to obtain this distribution. So it's really very inefficient in a sense that if you want to use this to compare to the data, well, you can still do it. But if you want to do a fit of Parton distributions using this, it's completely impossible. So you need other ways. And then there has been recently what is called the NQ-below calculation revolution. Sorry, it started 2015 more or less with the Higgs cross-section, and there are many processes that have been computed. But don't be cheat about this. It seems that many things were computed, but if you look at them in detail, they all correspond to processes which are like the 2 to 1. So it's proton into one object which typically has no core. It could be a W, a Higgs, 2 Higgses, 2 Ws, 2 photons, but still it's no color in the final state. So going beyond that is not simple. But people are already doing this. I think I will skip this. This is one interesting process, Drell-Yan. Drell-Yan has been computed 4 years ago at NQ-below, and here is the calculation with the 4 orders which are already known with the corresponding bands. And you can see that every time you go to a higher order, the band is being reduced, because in principle your uncertainty is reduced by going to higher orders typically. But you can also see that, for instance, if you compare NNLO to NQ-below in this region of small masses, there is no overlap between them. Like either something is going wrong there, or we are just using a wrong estimate for the uncertainty. So the uncertainty was possibly bigger than what we thought. Okay. Oh, the Yan is being measured with, in some cases, with a precision of the order of 1% or less. So you really need to reach this kind of precision. Yes. Yeah. Absolutely. Yeah. This is a key measurement. Actually, it's even relevant to check the luminosity of the collider, because you know it so well and you measure it so well that people some time ago people proposed to measure the luminosity of the collider by measuring radiance. Now, something which I find amazing is also done by people in Munich, is that I told you that the number, the magic number was 7. What we know now are the 3 loop amplitudes for 2 to 2. Okay, 2 to 2 processes, 4 particles, 3 loops are also known. And this is why I claim that the bottleneck in the calculations now is not the virtual corrections anymore, because the problem to do the calculation for double set production, die set production at next to the in order is from the real part, the subtraction part, because now the kind of singularities that appear there are amazing, incredibly complicated, so it will be very difficult to generate a subtraction term that matches all the singularities and that can be integrated. Again, I think what probably will become available first will be double photon production at 10 QBLO, which I think in principle can be done by using this space slicing method. Actually, it's a nice project, now that I think. Yeah.
Can you comment about the last one, violation of?
Yeah, okay, yeah. I left that, but I didn't want to say it. But no, we know that one of the key elements in order to be able to do this calculation is the fact that we can separate things in such a way that there is a subtraction term that contains all the same singularities as the process. And the key thing there is factorization, in the sense that you can factorize your matrix element let's say, in a collinear singularity, when you reach a collinear kinematic singularity. You can write it as the matrix element with 1 particle less time, which is called the splitting amplitude, or the splitting. Well, it turns out that when you go to this kind of orders, these splitting amplitudes, were in principle are supposed to be completely independent on the process. They depend only on. I think I put some. Yeah. Suppose that you have a process in which there are many particles in the final state, and this one emits a gluon. Okay. The idea is that when this gluon becomes collinear to this quark, this can be in that limit. This can be factorized in this way times the probability that this particle emits a gluon. And this is a splitting amplitude. When you take the square, this is a splitting, the alter Rayleigh Paris splitting function. Now, this is true at leading order, in a sense, true in a sense that this part is completely independent on what happens there. When it turns out when you go to something like QBLO, there is a color correlation between this quantity and this one here. So it starts to, you get a violation which is called a strict factorization. Strict factorization would be that. Here you get some color correlation, which makes the things much more complicated, because this kind of subtraction would be process dependent also. So you will have to adjust for that. That has to cancel when you put everything together, in principle. We expect that. But intermediate steps will be complicated.
Okay, so the problem is that you lose universality,
yes,
but you can still do it. I mean, there is an.
Yeah, in principle, you can still do it. I mean, there are some kind of proof that these things will cancel when you put everything together. The 3 loop, the 2 loop with an extra particle, the 1 loop with 2 extra particles, and so on. But there is no general proof, actually, of that. So it's, it will be a really, really tough to just to do the bookkeeping of all these terms, which are process dependent, will be complicated. Yeah.
Yeah, for a related question related to this factorization. So, of course, your motivation is to compare directly to experimental cross sections, which are infrared finite, so numbers. Now, of course, as a formal theorist, one sometimes has the freedom to just imagine and engineer some other finite objects. We like to call them also observables.
Yeah.
but okay, so as a premise, that idea. And so sometimes one common idea is actually to look at some ratios of
yes,
things where, thanks to the factorization, then by definition, the result will be finite. So I was just wondering to what extent is some similar ideas being used, that is, for example, one takes different processes that are being measured, but now let's say we give up the ambition to directly compare the number for each of those, but to look at some ratio. So then maybe conceptually it's simpler, maybe one could avoid to some extent this subtraction failure.
I don't think anyone has actually tried on that, because I think you probably can do that for very simple observables which are very inclusive, no? If you go to more exclusive things where you have many sets of many different cuts in the final state, then that would be probably very complicated.
So
but
again, this measurement function
yes,
that
exactly.
you mentioned, that one
Yes.
still wants to retain a lot of flexibility.
Yes, exactly. So then that's the reason why you don't do that analytically. But I thought about that about form factors, for instance.
Yeah, so
Form
like
factors, if you take ratios, they, yeah,
exactly. Take your whatever process it is and
yes,
divide by suitable form factors. At least conceptually.
yes,
sounds
no,
like a very
conceptually it's true.
clean,
Yeah.
clean object.
Yeah, yes, absolutely. Yeah,
Maybe some brainstorming.
yeah, that's nice. So now, since we are getting into the situation that we need to reach something of the order of 1 or 2% precision in these calculations, you have to remember that there is alpha also, not only alpha s, and that alpha s squared is of the same order of alpha, more or less. And electroweak effects can be enhanced if you go to the production of very heavy or very large PT particles. Then there are pseudo cofactors, logs of the energy or the transfer momentum divided by the mass of the W boson, for instance, that enhance these corrections quite a lot, because they typically get log squares, and then the corrections can be also very relevant. So today, if you think in terms of a perturbative expansion, you have to do expansion into couplings, okay? So you get the leading order, the full tower of QCD, the full tower of electroweak or QED, and then you get also the mixed QCD electroweak corrections. And that also involves very complicated calculations, and even looking at which is the evolution of the pattern distributions when you take into account these QED corrections. And this is something that people have been discussing over the last 10 years quite a lot. And there are many calculations that typically give corrections of 0.1%, but can be enhanced in some regions which are relevant from the experimental point of view. But I think this could be the message that when we are doing calculation for the LHC, we are attempting to get at the percent level, okay? And this is actually quite complicated.
Sorry, I was wondering about this because at the beginning you mentioned the pattern distribution functions. So this 5%, you expect this also to go down?
Yeah, but slowly. I mean, because the point is the following. When you look at this 5%, this is mostly related to the statistical uncertainties on the data. So what you do is you take the data, you produce a fake data set by doing statistical variations within 1 sigma, and then you do other fits. You do 1,000 fits, and then you find which is the typical uncertainty, statistical uncertainty for the distribution. But there are many other things which are relevant. For instance, if you change the scales for the process, if you do different parametrizations, and this has not been quantified so far, because they were expected to be of the order of 2-3%, and the uncertainties from the statistical part were larger. But now people are getting into that. So sometimes you get, from one fit to another, you get that this is a reduction in uncertainty because they got more data, but they also an increase because they are considering an extra source of uncertainty. So it will be tough. There are observables in which you can do these ratios, as you said. You can take the ratio between W and Z production, and this is where you can get below the 1% in general, okay? But yeah, it's there. Now, the splitting functions, as I told you, have been computed almost to the accuracy we need. It's already enough. We don't know the full set of NQ below splitting functions. Do we know the first mailing moments of them? But with some constraint, this is enough to do the evolution to NQ below. So in terms of pattern distributions, we are getting better, and even some people that are getting some moments at 5 loops. Let me think if I would say something about that. Then, even if you are able to do the perturbative expansion to a high order, we know that there are issues which are related to certain regions in the kinematical space in which the perturbative expansion fails. The reason is that when you reach the boundaries of a phase space, because of soft and collinear emission, even though these cancellations between real and virtual diagrams occur, since you are restricting very much the phase space on the real part, you get a kind of unbalanced cancellation of these infrared singularities. You cancel the 1 over epsilon square poles, but there are logs that remain there. For instance, typically, if you look at the production of a Z boson at the low transfer momentum, when you look at the calculation explicitly, you will see that there is a log of Qt over Q. Qt is the transfer momentum, Q is the mass of the cell. So if the mass of the set is about 100 and the Qt is 1 GeV, then this is a log of a large number that will be a large contribution. And the problem is not only that this log is large, the problem is that when you look at the expansion, you find that the log appears with a power which is 2 times the power of alpha s. So in some sense, the perturbative expansion is not alpha s, but alpha s times log squared. Okay, so the log can be large enough to cancel the small value of alpha s. And there are several cases in which that happens. And the only way to do to get the perturbative expansion again there, because the conversion is completely spoiled by these large logs, is by doing the resummation of these large logs to all orders. I am not going to get into the theoretical details for that. It's quite complicated, but today we know calculations that can do, for instance, the production of Higgs boson in different approaches, computing the cross sections to very small transfer momentum by performing the resummation, which is what is called next to little log. So you sum basically a tower of these logs up to a certain extent, and then you cut your expansion there in such a way that now your expansion is more convergent. The other thing which is very relevant is parton shower accuracy, because I've been talking about fixed order calculations in which you produce partons in the final state, but you know that when you go to the experiment, you don't see a parton. What you see is typically jets, hadrons, okay? So you need to mimic that transformation of the partons into hadrons, and this is usually done by starting with the parton shower. Parton shower is a key component of any Monte Carlo simulation, and so far, until recently, the standard parton showers were accurate only to the leading order, so to the first emission being treated correctly in the soft collinear limit, but not the rest. So now people are working now on trying to generalize this to reach next to leading order, and even, next to leading log, and now next to leading log. But I will skip that just to give you an idea that there is a lot of work on the parton shower in order to reach the same accuracy as it is obtained in the perturbative calculation. So I would like to finish by show you one example, basically, a good example about the relevance of QCD calculations, which is Higgs, the most relevant observable in the LHC in the last, since the beginning of the LHC. So this is a total cross-section, proton-proton into Higgs, as was computed at leading order, next to leading, next to next with some extra things, and in Q below, okay? This is the central value and what we consider, which is the theoretical uncertainty. And this is experimental result. So this quantity was computed by Georgia and other people in 78, okay? So people, of course, continue doing work, did the calculation at NLO, we managed to do it at NLO, and then now we know NQLO. Now we were lucky that by the time the Higgs boson was found with this cross-section, we had this calculation already, okay? Which was in reasonable agreement with the experimental data. Imagine that if we had discovered the Higgs boson in 81, okay, with this theoretical result. Of course, you can imagine thousands of papers claiming that there was BSM physics, okay, because there was a really big difference between them, but it was just the QCD, missing QCD terms, okay? So you can see that the expansion of this series, the conversion of this expansion is quite slow. Only from here you start to see that there is a reasonable convergence, I would say. So that gives probably a good idea of the kind of precision we need, but also of the size of the corrections we are dealing with. And the main reason for that is that this is a process which is being initiated, as I say, by gluon. This is gluon-gluon fusion into a triangle with tops, and then you get the Higgs. And the gluons are usually get very large corrections because of this color factor. Still, if you look at the global signal strength, if you analyze all the experimental data and compare to the theoretical calculations, both from Atlas and CMS, you see that this is the ratio between the experiment and the theory. You see it's very close to 1, so standard model-like. But when you look at uncertainties, you can see that the main uncertainty is still the theoretical uncertainty, okay? So we really need to reduce that, at least by a factor of 2 for the high luminosity LHC, because those statistical and experimental uncertainties will be reduced by more than a factor of 2. We have to match that. And this is a kind of anatomy of precision for Higgs boson production. So this is the uncertainty in the Higgs boson cross-section from the theoretical calculation, depending on the energy of the collider. Of course, we have to imagine that at some point there could be 100 TeV collider, but the LHC is somewhere here. Now, you can see there are many sources of uncertainty. One which is related to the PDF and alpha S. We are talking about this typical 5%, and this is particularly important when you get gluons. That will require more precise PDF and coupling, and for that you will need many theoretical development, but also many measurements of observers at a high luminosity in order to provide more precise data to feed the PDF with better precision. There are uncertainties which are related to the fact that for a long time, the calculation of this process to higher orders, gluon into Higgs, this is very difficult to do because there is a heavy top quark here, a loop. So what people usually did in the past was to do an effective field theory approach in which you can shrink this into a single coupling between gluon and a Higgs. It's quite accurate, but it's missing terms which are of the order of 1 over MT, and they are of the order of 1%. Then the mixed electroweak and QCD corrections were not very well known by that time, so we have a gauge boson here. For the PDF, you also need NQ-below PDF, which are missing. And one of the biggest uncertainties is related to the fact that we know the calculation up to NQ-below. If you want to reduce that, you have to go to the next order, and we probably take 10 more years. The good thing is that things are being done. People have already been able to compute this kind of diagrams, including the full top mass dependence, in order to reduce quite a lot this uncertainty. So this is much smaller than what it used to be. The electroweak, QCD electroweak corrections related to this kind of graphs had also been computed recently, and they have reduced, which was the original uncertainty, also by a factor of 2. So we are slowly getting into a reduction of these uncertainties, but getting the full factor of 2 by the time of the high luminosity LHC will provide precise data in 15 years. It will not be easy. I mean, it still will require a lot of work. I think we still have 1 minute wrong. Okay. So to finish, yes, what might be the next discovery at the LHC? I can also bet my salary on that, so who cares? I mean, I could bet my university salary on the precision thing and my CONICET salary on the next discovery. But I think the next interesting discovery of the LHC will be a double Higgs production. Double Higgs production is very relevant because when you look at double Higgs production, there are 2 ways at lowest order to produce 2 Higgses. One is by this kind of box diagram, which doesn't give too much information because it's the typical coupling of the Higgs to a heavy quark. But this diagram is very relevant because it includes the triple Higgs coupling. Okay, and this is the coupling which is relevant for the spontaneous symmetry breaking mechanism. It's the one that we haven't measured yet, that we can obtain by looking at the mass of the Higgs and the vacuum expectation value, but we didn't measure that directly. And we need to get into that because this could be very sensitive to new physics, of course. And so actually, probably the question is, what is the standard model today? This is the one you find in your T-shirt you can buy at CERN. But I think that the standard model today is more like this. Okay, so we are adding now extra effective field theory dimension 5. Well, they are negligible, but dimension 6 terms. And we try to fit the experimental results, trying to see whether we can find some non-zero coefficient from this extra dimension 6 Lagrangian. And that could include, for instance, things like that. They could include modifications to the coupling of the Higgs and the co-top quark by the 3 Higgs coupling. You can also even include a coupling like this one, in which you get TT bar double Higgs, or modify the single TT bar Higgs coupling and so on. So this is something that people have been studying for a while, and this is a measure that will be very complicated, but will also at some point will require precision. And this is also another example of a lot of work being done over the last, I would say, 15 years, in order to try to get to the highest possible precision for double Higgs production, which is not trivial, because now you have to deal with the box diagrams that contain heavy quark loops, and then you have to do gluons here in the virtual part, and that is very complicated. And when you try to use here an effective field theory approach, then the approximation is not as good as for single Higgs production, because the energy is much larger now. Now you are producing a system of 2 Higgses which has an energy which an invariant mass which is higher than the mass of the top. So the effective field theory is not so good. But this is a case situation in which there are very large uncertainties in these calculations, up to 18 or 20%. So of course, the experimental measurement will take quite a lot of time. But if at some point we really discover double Higgs production, we should be able to get a better description of this observable. So I think I will skip this part of the theoretical uncertainties. I just get to the conclusions. So to me, the most relevant thing is that there has been an amazing process in calculations during the last 2 decades. I remember being the first workshop in Lesuche in 2001, when people started to try to do next to in order calculations were very difficult. In the sense that being in a table discussing and nobody had an idea how to deal with these infrared singularities. And now there are several methods to do that. And this is actually driven by the LHC. I mean, it's not just an academic issue that I know how to do a two-loop calculation, so I will do it. It's because we really need that for phenomenological purposes. So improvements, there are more precise combined analysis of PDF. We have automation of next to in order. There are several processes which are being computed at NLO 222 and a few 223. We are getting NQLO for simple kinematics, Drell-Yan-like or deep elastic scattering, and the first set of splitting functions. We are starting to account for QED and electroweak effects. Resumation is also reaching, and Parton showers are improving in the logarithmic accuracy. But we are reaching new bottlenecks for large multiplicities. Large multiplicities could mean large, a number larger than 7 for the sum of loop plus the number of legs. But in principle, large multiplicities if you go to NNLO. Two-loop amplitudes beyond 2 to 3 is complicated. As we saw, there are already a few calculations in the 2 to 4 or the 6 particles. The real radiation is far from trivial, and I think this is the most complicated part. The treatment of numerical infrared singularities will be actually complicated and take a lot of time, and we need to get out of the box, because this idea that you can do this and put it in a big computer and let it run for years, it doesn't make much sense anymore. So we really need to find something more interesting. Processes at n cube below that go beyond Drell-Yan will require significant developments, and Higgs-Beer production will be fundamental. I really need more work there. And I didn't discuss, but we need a more rigorous treatment of theoretical uncertainty, in the sense that doing these calculations take a lot of work. When people finish these calculations, they say, okay, I have to quantify the uncertainties. Well, let's change the scales by a factor of 2 up and down, because I'm really tired of doing this. And then you put a band or whatsoever. But this is not a real rigorous treatment. So you have to go into some more statistically based treatment of theoretical distribution. There are a few people working on that, but this is not becoming still massive in the community. Nobody is really putting much attention. And I think we need to do that in the future. So I think I can stop here, and thank you for the attention.
I will use the benefit of using the chat. So you at the beginning you